It's an exciting time to be talking about SPHEREx. We've launched in March, and actually this weekend we'll complete our first full sky survey. And so SPHEREx is a unique mission. It maps the entire sky in spectroscopy. I'll tell you a little bit about how the instrument's designed, but I think it is a simple concept. And our core science goals and how things are going with the mission right now. So this little video just shows you what SPHEREx looks like. First of all, you can tell we're in low Earth orbit, and we're actually going across what's called the terminator line. It's the line between sunrise and sunset around the Earth pole to pole. And we always have the sun on one side of us with our solar panels pointed to the sun, and then the Earth below us. It's about the best orbit you can have for an infrared telescope going around the Earth. These distinctive cones that you see are a signature piece of SPHEREx. They're like cones your dog would come from after that. And they're part of the cooling system. Because this is an infrared telescope, we have to cool the instrument. And we do that passively by letting the heat escape out to the cold of space. Thermal photons basically bounce out between the shields, the nested shields. There's 3 of them. And that cools the telescope to low enough temperatures that we don't see it glowing in the infrared, as well as the detectors. When the cones disappear, here you can see the telescope. As Brian alluded, it's not a very big telescope. It's a 20-centimeter telescope. But don't let that small size fool you, because although the aperture is small, the field of view is enormous. It's 3.5 by 11 degrees, giant field of view, very large photon gathering capability, but small aperture. The light comes in through this telescope there at the top, bounces to 2 detector focal plane arrays, one here at the top and one here at the bottom. And this one at the top is cooled to the lowest temperature. Okay, so here's what that system looks like altogether here. Cutaway view of the telescope. And so as I mentioned, the telescope here, 20-centimeter aperture, but huge field of view, rather coarse angular resolution, 6-arcsecond pixels. So that's pretty big for astronomy. And the reason is we need to get enough sensitivity. We're really sensitivity driven. And so, compromise is angular resolution, spectral resolution, sensitivity. Sensitivity is going to push you to have, worse angular resolution and spectral resolving power. The passive cooling system, as I mentioned, there's 3 stages. Thermal light bounces out. Here, these shields protect the instrument from the Earth glowing at, basically room temperature below us, and then the hot sun keeps the instrument shaded while letting thermal photons bounce out in 3 stages. So each one of these stages is progressively cooler. The telescope is kind of the 4th stage. It's suspended and it's also radiating out. And so the passive cooling system actually achieves a temperature for the telescope that's more like 62 degrees Kelvin. And then there's a 5th stage, which is this radiator panel, which just cools the longest wavelength detectors. And it actually now achieves 45 Kelvin in low Earth orbit. And so the advantage of this design, there's no coolants, no refrigerator, no consumables. It just runs on the coldness of space. The telescope shown here is a wide field 3-mirror telescope, and the field of view split into 2 focal planes by a beam splitter. Each of these focal planes has 3 4-megapixel Hawaii infrared detectors. And the way we do spectroscopy is kind of embarrassingly simple. And the embarrassing part is how long it took for us to think of it. So basically the idea is we just put an interference filter on top of the detector. And the interference filter is made such that the interference filter just passes a narrow band of wavelengths. And these filters are crafted such that the thickness of the layers vary so that the wavelength peak response varies over the filter. So you can sort of see that in reflection. If we're able to see in the infrared with your eyes, you'd see through this and see different wavelengths just varying continuously across the filter. These filters are modest resolution. varying between about 35 and 130, depending on the band and the science we're doing. And again, higher resolving power is always helpful, but there's a sensitivity penalty that you pay. SPHEREx operates by basically taking a bunch of pictures, and that's actuated by an agile spacecraft here that, rapidly points and then stabilizes the observatory to carry out our observations. Okay, so that's SPHEREx in a nutshell. Here's how the spectroscopy works, as I mentioned. So basically, every picture we take, a source will land in reflection and transmission in one place on the focal plane. And so then we see that source at that wavelength. And that's how we do spectroscopy. Why is this a good idea? Well, it would seem like a bad idea from an astronomer viewpoint, because generally you want all your pixels on the object of interest, and you don't want to waste them looking at other things. But with SPHEREx, the object of interest is really the whole sky. So while our source is being observed at a couple wavelengths, all the other pixels are doing work observing the rest of the sky at other wavelengths. And as I said, it took us quite a while to realize this. And the way we take spectroscopy then is basically take a series of images. Here you can see the pointing rapidly sped up. But after we take 51 of these images, we get 2 per pointing. We get 102 colors, and that's a complete spectrum. Each of those images takes about 2 minutes. And so that gives you some idea how it all works. After inventing this idea, we found out that we hadn't invented it, that it's actually been used on planetary missions to map very effectively and rapidly the spectra of planetary surfaces. Oh well, it's still a good idea. Okay, so here's how our observations take place. Because we need to always have the telescope avoid seeing the Earth, we can't tip too far down, and we don't want to see the sun, so we can't tip too far towards the sun. That leaves us with a kind of semicircular region where at any given moment, we can point the telescope. And so what we do is you take an exposure, and then the most efficient thing to do is to move just a resolution element, about 12 arc minutes, take another exposure, and do that as much as we can. And while we're doing that, we love the Earth, but it's kind of getting in the way here, because as we're going around the Earth, it's coming up into the telescope. So every so often we have to do a large slew and kind of reset our zone of avoidance and then go back and continue that process. And so you can see this kind of leaves a giant jigsaw puzzle on the sky of how we're going to cover the sky at all these different wavelengths. But our survey strategy is very detailed and accounts for all these things, and it does close and tile the sky very efficiently after about 6 months. So, as I mentioned, each of those exposures is about 2 minutes. We go around the Earth a little bit longer than 95 minutes. So that's a very sped up image of how we cover the whole sky. Here, this is going whizzing by weeks at a time in a second. But we basically are observing a great circle, roughly 90 degrees from the sun, and that circle precesses. The orbit's always locked along the sunrise-sunset line, just because of the lateness of the Earth. So the orbit's engineered with that in mind. And basically, as the Earth goes around the sun, that great circle rotates. And after 6 months, it closes, and you get a complete map of the sky. So there it is after 6 months completing the survey. The other thing is that, yes, question?
How do you maintain it in that orbit? How do you maintain it in the meter orbit?
Yeah, so the orbit we have no propulsion, so we don't do any orbital maintenance. It's just basically if you hit the orbit accurately enough, the oblateness of the Earth precesses the orbit naturally.
There's no reaction wheels?
There's reaction wheels to do the pointing, but there's no propulsion to adjust the position of the orbit. The other thing is with these circles, they always cross at the poles, the north and south ecliptic poles, which are 90 degrees from the sun. So we have these special regions where we can do deeper observations, and we take advantage of that. So we have these 3 modest questions that we want to address with SPHEREx. How did the universe begin? How did galaxies begin? And where's the water in our galaxy? And so I'll briefly discuss how SPHEREx addresses these 3 pedestrian questions, and I think in powerful, unique ways. And as a byproduct, we created this all-sky spectral survey, which is a really, it's a new thing in astronomy, and there's a bazillion things that one can do with that as well. And one of the important things we do is we get the data out to the community rapidly within 2 months of collection so that the general public has access to it. So on to our first theme, how did the universe begin? Well, as Brian alluded, our universe began in a hot Big Bang, and current theory is that in the first moments after the Big Bang, the universe went through this rapid expansion called inflation. And at that early time, the universe's energy was enormous. We're at the 10 to the 16 GeV scale. And this energy scale is really beyond what we can probe with the standard model of particle physics or particle accelerators around by orders and orders of magnitude. Maybe someday that will change. But for the foreseeable future, if we want to explore this epoch of what caused this expansion, which is probably driven by exotic physics, the universe itself is probably our best laboratory. So what can we say with the universe that can probe this early epoch? So SPHEREx is looking for a property of inflation called non-Gaussianity. And so one of the predictions of inflation is that the fluctuations we see in the background are almost perfectly Gaussian, but maybe not quite. And what I mean by that is if I look at the microwave background here, this relic of a photon background, furthest back we can see with photons, those hot spots and cold spots are reflecting the underdensities and overdensities produced by inflation. And I can make a histogram. I can do better statistics, but let's just make a histogram. And what we find is that we just histogram the brightness fluctuations. Those fluctuations fall on a Gaussian curve. It's exactly Gaussian to our ability to measure it. And that already tells you something special is going on because most processes in astrophysics are very much non-Gaussian. And here is a signature coming from the early universe that's basically perfectly Gaussian to our ability to measure. And so the microwave background has been studied extremely well. Planck is the most recent all-sky measurement. And what we're looking for is some departure from non-Gaussianity, because depending on your model of inflation says first order is Gaussian, but there should be some small departure. And that departure is very interesting. And there's no detection in the CMB. And what's worse is now this is very close to cosmological noise. And what that means is there's only so much independent information we get on the sky. The important thing here is that the microwave background, when you look on the sky, it's really a 2D picture. So that's the available information. But those hot spots and cold spots in the microwave background are due to overdensities and underdensities. And those overdensities go on to seed large-scale structure, which is traced out by galaxies at later times. So, yes.
A quick question about the Gaussianity. Is the mean width of the Gaussian what people expected?
Well, it's basically equal. It's Gaussian, and then the width is telling you the anisotropies in the CMB.
And is that what is expected?
Well, there's been a rich study of the spectrum of the anisotropies, and I would say the takeaway message is that they're consistent. Maybe they help build the lambda CDM standard model of cosmology.
But it's a free parameter, we have to measure it. It's not predicted in a theory.
Right, but I guess I'm asking, what is it telling you? I mean, you're not getting a beyond Gaussian signature. So I'm asking you what information are you extracting from the Gaussian signature?
Yeah, so the way people extract that isn't with a histogram, it's by taking a spatial power spectrum.
Yeah.
And there's features in the power spectrum.
Yeah.
And those are sensitive to various physics mechanisms that have to do with the state of the plasma and the universe at that time. And there's acoustic peaks, so there's lots of cosmological information. And that's all telling you about the structure of the contents of the universe. But it's all Gaussian.
Are there independent measurements of that width from other experiments?
This is Planck is the best. And the measurement of Gaussianity, as I said, it's really limited by the cosmological noise or close to it. So this 3D picture with large scale structure I think you can see, has got actually a ton more information. And so what we aim to do with SPHEREx is use this large scale structure to do a much more powerful test of non-Gaussianity. And more to the point, the limits here from the CMB are just a little bit too high to probe interesting models of inflation. But if you can do a factor of 10 better, that opens up an interesting parameter space.
Excuse me, could I ask you about, sorry, I'm not a scholar of this physicist. What aspects of non-Gaussianity are you hoping to understand? Do you want to understand, say, the skewness, or do you want to understand details of the distribution?
Yeah, there's different statistics, and in principle, different measures of non-Gaussianity are telling you even more about inflation and are very interesting. We're kind of probing the most basic one, which is called FNL, but there are other measures of non-Gaussianity. It's kind of telling you this, if you like, the skewness in this histogram, the abundance of overdensities and underdensities. But there's, in principle, if you have the sensitivity to do it, a lot more information you could gain.
But anything that relies on the power spectrum is implicitly assuming it's Gaussian. Now, for the Gaussianity captures all the physics, there are probes that obviously you don't talk about that are sensitive to things that depart from that, in which case, strictly speaking, power spectrum is not a complete description.
Right, right. So, right. Did you? Yeah, so, yeah, when you take a power spectrum, you're implicitly assuming that's all the information.
We need measure the second one.
No, I mean, so I guess the question is what is exactly being measured, and most of the work has been on low order endpoint functions.
Yeah.
So the 2-point function,
Yeah.
but also 3-4-point
Yeah.
function. There is interesting physics in the tails, but
Yeah.
that hasn't, there are recent papers, but that hasn't really been studied too much. I mean, there are some attempts to measure that, but most of them focus on low order endpoint functions.
So when they're saying measuring the power spectrum is assuming Gaussianity, you mean just because you're just measuring the second one?
Well, the 2-point function, you can still measure it, just treating it as a 2-point function, just measuring the 2-point function.
Yeah.
And then if it were Gaussian, that would be all the information there. Essentially,
Yeah.
it's non-Gaussian. So if you want to get all the information, you would have to measure all the higher order
Yeah.
endpoint functions. Typically was to measure just 3-4-point functions.
Thanks.
Some of you may be aware that there's other probes of inflation going on in this room. The microwave background has another constraint of on inflation, which is probing the amplitude of a gravitational wave background produced by inflation. And this gravitational wave background can induce a characteristic polarization pattern in the microwave background. These B-mode swirly patterns that are parity violating, they look different in a mirror, unlike these E-mode patterns. And the lack of detection has the constraints have now gotten extremely good. So these are the latest from data taken with the BICEP experiment from 2018, these blue ellipses. What you're seeing here on the y-axis is the amplitude of the gravitational wave background. Again, no detections, constraints. And on the x-axis is the index of fluctuations. So inflation predicts basically a characteristic shape, which is scale invariant, but not quite. Scale invariant would be 1, it's slightly redder. And basic models of inflation, single field models, generally have a relationship between departure from scale invariance and the amplitude of the gravitational wave background. So you see them here by these lines. These are some families of inflation models. And the really interesting thing is that now all these models, at least if NS hasn't moved, are ruled out at better than 2 sigma. So these would be popular, heretofore popular models of inflation, and they are all excluded. So non-Gaussianity is complementary to these kinds of measurements. And you can see here that the CMB has plans to push down current errors another order of magnitude in the coming decade with the combination of BICEP array with the South Pole telescope and at the South Pole, and in Chile, the Simons Observatory. And so it's always good to have 2 experiments, and we're racing to improve this further. With the large scale structure, we've designed SPHEREx really to do this science. And what that means is here are some other large-scale structure surveys from space, and they're really targeting the properties of dark energy. And so they're focusing their spectral power at redshifts where one expects to see the signature of departures from, the equation of state of dark energy. So here's Euclid targeting the redshift 1 to 2 area, Roman doing a much smaller area, much more deeply than Euclid. And SPHEREx, to do non-Gaussianity, we really want to cover the whole sky well. We want to recover large angular scales, large spatial scales, and have a large volume. And so we're lower redshift because of the smaller telescope, and going out to redshifts where our accuracy gradually reduces because of our limited sensitivity. And so what we're after with SPHEREx is of order 500 million low accuracy redshifts and 15 million high accuracy redshifts to go after non-Gaussianity, which is complementary to these searches for dark energy. And so what the bottom line here is, non-Gaussianity is sensitive to whether, mostly sensitive to whether inflation is driven by a single field or multiple fields. So those models of inflation I showed you that were constrained from the CMB are single field models. And on this graph, non-Gaussianity here is on the x-axis, and this is the running of this change slope curvature of the spectral index. All the single field models lie on the y-axis. They basically predict negligible levels of non-Gaussianity, less than 1%. But if inflation is more complicated, if it's a multi-field description, the interaction of those fields generically predict levels of non-Gaussianity parameterized by this value FNL of order unity. So that's where we need to get the errors down from 5 from the CMB with this big blue ellipse down to order 1/2 with a large scale structure. And so we're using 2 statistics to do that, but that small little red ellipse there represents our sensitivity. Now we don't know where this ellipse is going to fall within this big blue ellipse. This point's just been picked arbitrarily. If we did land here, that would be very interesting because we would rule out basically the notion of single field inflation. If this landed on the line of single field inflation, it wouldn't rule out multi-field inflation, but it would rule out a huge parameter space. So either way, it's really important, and putting the 2 measures of inflation we have from the CMB and large scale structure together gives you a much more complete picture. Yes.
Are these forecasts only for local non-Gaussianities, or?
Yes.
And what do you expect to find for equilateral and orthogonal?
Yeah, we have some constraints from like equilateral. They're not very good though.
Is it still roughly what, like, I don't know, maybe more than planned, like other LSF missions, or do you get within the order of plan?
I will provide you a number afterwards, but yeah, they're not great, unfortunately. And it just shows that they're really hard to measure.
Yeah.
Okay, so our second theme is how do galaxies begin? And galaxies, were born out of this early universe, forming from originally neutral hydrogen after the CMB. And so this process of the first galaxies and stars turning on is called the epoch of reionization, where those stars and galaxies, the UV photons, ionize the gas between the galaxies in the intergalactic medium, leading to our current state of almost perfect ionization between galaxies that we have today, up to a redshift of about 6. So if we want to understand this process, so galaxies are born here, and then galaxy formation continues. Star formation in galaxy peaks about 5 billion years after the Big Bang, and it's been on a slow decline ever since. Now, the typical way that astronomers study this, and it's been studied very well, is to take a big telescope, look at the individual galaxies, look at their properties, distances, metal contents, what the stars are like in them, and so forth and so on. Obviously with the 20-centimeter telescope, we're not going to be doing a lot of that. What we're doing instead is a very complementary measurement of basically measuring the total background light from those galaxies. So in other words, all this light production piles up into a background glow over the sky. And the glow is proportional to the total light produced at each redshift epoch added up. And it contains everything, so the emission from these early galaxies piles into the extragalactic background light as well as this brighter time of galaxy and star formation that happens at later times. And so this is a very unique measurement using the background light and quite complementary to the, galaxy by galaxy kind of measurement that we do. And just to give you an idea how this works, okay, well, so one question is why don't you just measure the total light? So we're not actually doing that. We're not measuring the total light. And the answer to that is given by this picture. This is a picture taken, obviously, in northern climes, just after sunset. And this stuff here that you see is not light pollution. It's actually scattered sunlight coming from dust in our solar system. It's called interplanetary dust, and the light produced here is called the zodiacal light. And this stuff is really bright. It's a couple orders of magnitude brighter than the total extragalactic background light, and it's difficult to separate. You also see this stuff. Sorry for the resolution of this picture, but that's our galaxy. So that's another foreground. And I've tried with Brian, to separate, put constraints measuring just the total brightness, and I can say it's not an easy business. But we can use a property that this zodiacal light is very spatially smooth. And so that brings us to a new method, which is given by this picture. So this is a map of an extragalactic field. You can see it's a pretty large map. It's actually made in the far infrared with an observatory called Herschel. And it doesn't have great angular resolution. And so if I point to a given region of this map, generally speaking, I can't say whether there's one galaxy in that pixel or two or three. Some cases, yes, you could say there's a galaxy there, but for the most part, it's pretty confused. So that limits what you can do with it. But I think if you just squint your eyes, you can see there's a large scale pattern here, and that's due to the fact that galaxies aren't randomly distributed; they cluster together because they're in common dark matter halos. So this quilty pattern you see is due to the fact of this galaxy clustering. And so this map contains a ton of information without detecting the individual objects. It's telling you how galaxies cluster and the brightness of that clustering. There's also a nonlinear clustering that tells you how galaxies turn on within a dark matter halo, and then a shot noise signal, which has to do with the distribution of point sources. So there's a ton of information. And the interesting thing here is in the far infrared, there's a redshift correction such that the light from a typical galaxy piles up into the far infrared. And so at this wavelength, you can see pretty far back in redshift. That's both a blessing and a curse. And in this case, it's a curse because it's hard to separate out the redshift history if you only have a few bands, because all those redshifts kind of look to first order, similarly bright. And so while this map actually does an amazing job of measuring like the spatial power spectrum from these various components, it's not very good for telling you the redshift history. So what we aspire to do with SPHEREx is basically this process. We're going to take those deep field regions, measure the information, the spatial information available in the map, not measuring really the individual sources themselves, but do this in 102 wavelengths. And those wavelengths are well suited to constrain the history of galaxy formation as well as this early period of time from the epoch of reionization. And the method is very powerful because on large scales, the signal you're looking for, the clustering signal, is proportional to the total emission. So it's telling you the emission from everything. Everything that feels the influence of gravity that emits light, you measure with this clustering measurement. And so, it's emission from all galaxies, including dwarf galaxies if they're important. You're measuring that total signal. Diffuse components, like from strip stars, at more recent times, maybe even exotic things like dark matter decay. It's all in the map. And here's a forecast for what is shown here. This is basically the clustering power. So this is the signal that's proportional to the total light emission. And it's spread out here in wavelengths at a characteristic angular scale that is proportional to the clustering signal. And here's a model that shows the contributions from galaxies up to redshift 0. And so right off the bat, interestingly, here are short wavelengths and out here longer wavelengths with Cyber and Spitzer, the total signal's apparently brighter than just the total light predicted from galaxies. So something else may be going on. So the model in pink here is this idea that galaxies also have a stripped star component, which can give you additional power. As we go deeper in redshift, the signal goes down. And then in blue, here's a range of possible models from this epoch of reionization. And you can see here characteristic signatures from the fact that the universe is becoming ionized. So there's this Lyman break, first of all, and then the Lyman alpha bump. These are all characteristics, fingerprints of hydrogen. And way down here at the bottom is our sensitivity. The top line is our sensitivity in each individual spectral channel, and bands are if you co-add those together. And so, at least in terms of raw sensitivity, we can go all the way down here at the bottom of the reionization models. Now, there's a lot to worry about before we get down there. First of all, there's this bright foreground, and you have to worry about systematics and so forth, but the raw sensitivity is pretty awesome. Okay, and then our third theme, where's the water in our galaxy? Well, generally speaking, the water in our galaxy, well, we're interested in this question on Earth because water is so closely associated with life on Earth. And if you go to the South Pole, where all the water's frozen, there is not very much life unless it's flown in on an airplane. But at the edge of Antarctica, where there's liquid water in oceans, life's abundant. So where did that water come from? Well, that water on Earth had an interstellar origin. And the water in the interstellar medium is not in the form of vapor or liquid. Predominantly, it's in the form of ice. And those ices form on the mantles of interstellar dust grains. And they're important in this process of early star and planet formation because, well, first of all, it provides the building blocks, the initial building blocks, perhaps for life, but it also, congeals this material as protoplanetary disks are forming, allowing the material to stick together. So water is important. And the way we measure it with SPHEREx is we do absorption spectroscopy, where we have a background star behind a cloud and can measure the attenuation versus wavelength of that light passing through the cloud. And there's distinctive fingerprints. There's this very broad feature here from water ice, but there's other features too. There's fingerprints from carbon dioxide, carbon monoxide, as well as methanol and some stretched modes. So all these materials are basically organic as well, and their abundance is quite interesting. So with SPHEREx, what we want to do is we want to make a large survey of the abundance of water ice. Yes.
I mean, there is like this cloud of ice around the solar system, or cloud. How would that? We don't understand that well enough. Would that introduce any serious systematics, or not really because it's too close, maybe?
Well, I think it's an interesting question. I think the zeroth order answer is I'm not sure. I think it must depend a lot on whether the ice is in the form of, discrete objects like comets, or whether it's in a more diffuse structure where you could potentially see its influence. And so this abundance of ices have been studied in the interstellar medium with other telescopes, but it's of order, several hundred objects. With SPHEREx, we want to make a giant survey, cover the whole sky with a huge database. And this shows the density of sources that we can predict prior to SPHEREx. We basically plotted sources here which are embedded. You can see the degree of embedding by this number AV. Isolated and sufficiently bright that we can detect them with a signal to noise of 100 per channel. And there are a lot. This is almost 10 million ice targets distributed over the sky. So this, in principle, will all turn these into ice abundances. And so this is really just an unprecedented data set. Okay, and then in the business of doing this, of course, we're going to make a spectral map over the whole sky, which every place you look on the sky, there's 102 wavelength channels. And that's a unique data product. There's a bazillion things you can do with it, the measure properties of stars, clusters, even asteroids and comets. And all sky surveys have had a great track record in astronomy of having enduring legacy value. I think people are still using IRS these days. And we expect many exciting discoveries will come from the community using this data. And so we are putting out the data very rapidly. Within 2 months of when the data is collected, you can go up and, look at the data yourself. Okay, so a bit on state of SPHEREx now. So this picture was taken in January this year, and this is SPHEREx traveling by truck from Boulder, Colorado to the Western Range. This is arrival at Vandenberg, near the town of Lompoc, on the central coast of California, avoiding Los Angeles because of the fires which were raging at the same time. SPHEREx is back here at the end of the truck. After that, while that was arriving, this is our booster line on a different project. I think this was its 4th flight, and here it is coming down about the same time we arrived. And that's just the way the space business rolls these days. Some assembly was required. Here's SPHEREx getting put together in that high bay space. And then there were a series of delays that happened. If you were following the launch, you may have noticed one frustrating day after the next, things were delayed. So our team diverted themselves with the many pleasures of Lompoc. Wine tasting was my favorite, but some people jumped out of airplanes. And it is actually a really delightful area. But finally, we were integrated. And here you see SPHEREx at the top. Here's the cones. This is the spacecraft. This is a standard ESPA ring. And here you see 4 other satellites. So this is another NASA satellite that wanted to go in the same orbit. It's a heliophysics array of satellites, 4 satellites called Punch. And so we were co-launched together. And even so, the combination of us did a very poor job of filling the available space here in this enormous fairing from Falcon 9. So you could literally put 2 of us in there, we would fit in the total fairing. Yeah, this is really, really amazing. And we were so enraptured with the enclosure encapsulation of the fairing, we did it twice. That was not intentional. There were some problems, but never mind. Here you can see it going together, and quite a
What's the shroud material? Is it?
It's very lightweight, and actually it's also recovered out in the ocean after the flight and reflown. So this is also, it's not its first rodeo. Although you get your own sticker. Okay, so there's a subset of the launch team. And actually we're here on the recovery pad where the booster comes back down. And obviously that's the vehicle ready for launch. This is the nice sunny day of Saturday. Of course, we didn't fly on that day because things were delayed again. But people in red shirts are basically on the SPHEREx team. People in blue are from Punch, and people not wearing shirts are either from NASA or from SpaceX. Cool people wearing glasses are from SpaceX. And you can see people you know. A key part of the success of SPHEREx was actually having young scientists at Caltech involved in the design and testing of SPHEREx. And they have unique experience here because they have built for their PhD projects, cosmology experiments and made them work. And so they have that end-to-end experience, and you put them together with engineers from JPL, and good things happen because they have really complementary skills. And so the teamwork here was really amazing, and these people are totally superheroes experience. Okay, so here's the launch. Sorry, there's no sound.
Turn on the volume on your computer.
Oh.
SPHEREx and Punch on their way to map out our universe like never before and revolutionize space weather forecasting.
Stage separation confirmed.
And ignition. Stage 1 for back startup.
So here you can see the upper stage going.
Coming up next, we will see fairing deploy, and that's when the 2 fairing halves will separate and expose SPHEREx and Punch to the atmosphere of space.
Fairing separation confirmed. In about 30 seconds, we will have payload deploy of SPHEREx. SPHEREx separation confirmed.
SPHEREx is drifting away from Falcon 9's second stage, confirming deployment. The mission isn't over yet. Falcon 9 second stage is still carrying NASA's Punch mission.
Separation confirmed.
Wow, look at that. To actually see them, that's great.
Okay. Yeah, so launch was a stressful but ultimately successful experience. This shows the early commissioning phase. So here's the temperatures you can see. And at the beginning here, we're degassing the optics and the experiment. So basically, we're pointing inertially going around the Earth. And so the radiation from the Earth is alternately heating the experiment, driving off water, because we're trying to detect water ice, and we don't want any water ice on our optics. And so this process is was a new process, actually, but it worked extremely well. We have no detection of water ice on our optics. We heated up the mirrors. Well, we popped the lid here, and so you can start to see things cool. We were heating some of the optics above their surrounding environment to keep water off of them until we got down below 150. And then here you can see the temperatures equilibrate, and then actually they're controlled to, like 10 microkelvin, incredible stability. So the telescope here is running at 62, and the longest wavelength detectors are controlled at 45 Kelvin. Quite cold for lower orbit. I could talk all day about the in-flight performance, but if I had to summarize it in one slide, this would be it. So this shows our sensitivity on the all-sky survey from the flight data. And so these are in units of magnitude, up is good. And so you can see the blue curve here is our 5 sigma per channel sensitivity per spectral band. So there's 102 of those points. Our pre-launch predictions made in 2018 are shown in the band. And so this is NASA acronyms, but the best case performance is this so-called CVE, and kind of required performance. Well, we'd be disappointed performance is the MED, and then our requirements all the way down here. And you can see we're basically hitting our best case scenario, which is pretty surprising because some stuff happened. We didn't get the exposure time we wanted in terms of once we worked out the full survey. And so a couple of things came out better than expected, such as the optical efficiency of the detectors and filters. So the instrument's working great. This feature here is due to terrestrial helium emission. And so it turns out the Earth has helium in the upper atmosphere, and that line emission is brighter than the astrophysical sky. And so the photon noise from that emission causes this one band to be less sensitive. The rest of the band here is basically limited by photon noise from the sky itself. Here's a movie going through our wavelengths. And so this was taken, put together a couple of weeks ago, and you can see a lot. So what you're seeing here is the current maps we have stepping through wavelengths, going from the short band out to the long band. These areas have very large pixels, and that's because we hadn't quite mapped them yet, but we will complete that come this weekend. There's some frames here that have poor astrometry because of the confusion in the galactic center, but we have the data. That's just an artifact. You can see the Magellanic Clouds out here. And then what I think is cool is you can see the galaxy getting narrower and narrower and narrower. And at the longest wavelengths, you can start to see the center of the galaxy peek out of the disk. And there we go again, cycling back to the short wavelengths. You see this dust here in the plane of the galaxy. You can see that go away. Here are the Magellanic Clouds. You can't really see it with your eye, but there are line and other spectral features that pop out here. The most notable is the PAH, polycyclic aromatic hydrocarbons, coming out at 3.3 microns there, that fuzzy stuff. A lot going on. Yes.
Few straight lines that sometimes pop up like versus this.
Yeah, so there's these kind of features here. Those are artifacts, and some of it's terrestrial emission. So we occasionally see emission in the upper atmosphere from aurora and things like that due to the high solar activity we have now. So the Earth's atmosphere is not even at 650 kilometers, is not perfectly dark. Okay, here's a composite image made at 4 bands. So they're made at 4 bands because we're really hoping that people will be able to see in more colors than 3 bands. And maybe you'll be able to get to 102 like SPHEREx. So we have versions of this with like 7 bands. It's kind of ridiculous because your eyes only really see in 3 colors. But you can see here the distinctive features from this green stuff is really pHs. So that's all this dust emission surrounding the planet galaxy. And mantis shrimp can see in 16 bands. So our images would be more appreciated by people. Okay, just a few things in terms of how things are going with our early returns on our various themes. So one thing we're doing is looking at using our spectral information to determine the redshifts of galaxies. So we need that to create this large 3D galaxy survey. And here's a stacked spectrum of DESI-BGS galaxies. And so there's like 6,800 galaxies that have gone into this stack. But you can see, you know, this very prominent 1.6 micron bump that comes this stellar feature. And this continuum feature is very powerful for measuring redshifts. Here you see pHs popping out. There's also some weak lines that are evident. And so this is what an average galaxy, you know, looks like from the stack. And it, you know, SPHEREx is doing a beautiful job determining its spectrum and therefore its redshift. You can see also here the line features. As I mentioned, they're not super powerful for this on average, but they do have redshift information that can help us sharpen up our redshifts. You can see at the long wavelengths, our calibration is a little bit off in wavelength, so we know about that. We can also do something which is called a self-organized map, where we divide galaxies up by their properties and then look at their spectra in aggregate. And again, these are galaxies that we already know their redshifts. So this is kind of a training set that we use to tune up our redshift algorithms. And so these self-organizing maps, here's a couple of that show their properties in terms of the number in each bin and their redshift and their brightnesses. But if we pick, you know, some cells here, we can investigate the properties and tune up our templates. And already we've seen that the data-driven templates do a bit better than the templates that we had prior, mostly because this infrared region is not, you know, incredibly well measured. So here's 2 different kinds, and you can see here the prominent lines for this type of galaxy and the more general continuum information that we use for the redshift fits. So that's coming along, working well. I mean, obviously, we're still in early days, but that's very encouraging. This is the deep field map that I mentioned. And so this map has of order 50 times the depth in terms of hits compared to the all sky fields. And so we're, you know, have a lot higher sensitivity. What you see popping out here are basically stars, those bright objects. So the underlying galaxies and their clustering is buried underneath these stars. They would have to be masked and removed. And we also have this interesting object, which turns out to be in the middle of our field. It's the Cat's Eye Nebula. Great. Not really what we're looking for, but we have very exquisite measurements of its many lines and so forth. Yeah, looking back at us. And what we hope to do with this, the first thing we want to do is basically take our maps. The easiest thing to do is to take our maps and cross them with known galaxy redshifts. And that distribution of redshifts is correlated with underlying structures. So the structures in the map should correlate, and at every wavelength and every redshift slice, we get a power spectrum, and we see that emission across our wavelength band. So this is a simulation, and this is picking one L-bin. So this is at fairly high, small angular scales. So this is what you're seeing really here is that Poisson noise, just the like shot noise, individual sources. And here's the wavelength, and here's the redshift. So this is going in redshift slices from 0 to about 2. This brightness is telling you the total brightness of in redshift slices, which is interesting. And you can also see some distinctive features predicted from pHs, some hydrogen lines, and oxygen. And we can do this at a variety of angular scales. So here on large scales, this is the clustering signal going to nonlinear clustering going to shot noise. And so these are all predictions. But I can say we have done this with the real data, and some of these features we already see, which is really exciting. And then our third theme is the abundance of various ice materials in the interstellar medium. And this is a star-forming region, Cygnus. And it's done in 3 colors again. And you can see absorption, characteristic absorption here. And I don't, by design, have a map that shows you the abundance of water ice and other ices, but we see that very clearly. And our science goal is to measure the abundance of ices in 20,000 sources. And this map alone has over 100,000 sources. So kind of crushing our science goal just in this map alone. But writ large here on these structures, we can see characteristic absorption from water and other ices, and we can see the variation. And that is coming soon. Okay, so in summary, SPHEREx is up in space. We're just about to finish our first all-sky map. Ultimately, we plan to have 4 maps in our baseline mission with the core science results coming out 3 years after launch. Observatory and instrument are all in happy state, working beautifully. We're looking forward to executing our core science themes. There are multiple studies and very powerful. I didn't mention this, but we also have 3 legacy science programs to study the properties of solar system objects, clusters of galaxies, and stars that contain host stars for exoplanets, because the properties of the stars are important, as well as low mass stars. So that's also happening. And SPHEREx's science range is incredibly broad, going from Earth's atmosphere. Our first community paper was on Earth's atmosphere helium emission, and all the way up to the dawn of the universe. And so we're very excited, and thank you very much.
Yeah, thank you. It's wonderful. On the slide where just a few slides ago, where you were looking at the kind of cross correlation between the extragalactic background light you get and the galaxies. You can look for a source of say, light EBL from particle decay, for example, some dark matter.
Correct, yes.
How would that look in that? So you showed the ones where, the lines of, the lines showing up and helium lines showing up, but what would that actually look like?
Well, presumably what you would see is.
So I have a high redshift decay of some particle, for example, and it's on line. And so we redshift it down into the band you're looking at, right?
Right, and so you would see that as an additional line, basically, here.
So it would map that way, just the way the atomic lines.
Yeah. By the way, this kink here is due to the fact that our resolving power changes at that wavelength. So that has nothing to do with the redshift evolution. It's just the way our wavelength map goes.
So that line shows up because you have the emission in those, like H alpha, for example, or the proven lines of oxygen. You have that at various redshifts.
Correct.
Right? And so that's why you see that.
Right.
But if we have a narrow regime of redshift where particles decay.
Well, then it would just appear as, some limited streak.
Okay, thank you.
Yeah.
So once you've finished your 4 maps, what happens next? Is there a possibility to just keep going and make it deeper, or?
So this is an Explorer mission, so we have to propose a baseline. And so the baseline is 2 years with an additional year of data analysis. There are mechanisms for NASA to decide to extend the mission if they so choose. There's nothing technically in the instrument that prevents it from operating longer. And hopefully NASA will continue to extend it as they do other missions, but it's their choice.
In the study monoclinic, is there an idea of whether it could use to look at the 4-point function of primary perturbations, or is it also as hard as it is for the spectra?
the question is whether we could use the 4-point function.
Yeah.
Perhaps in theory, we have our hands full, I'll say, with the 3-point function as it is. It's there aren't a lot of tools available to analyze that data. We had to develop them from our team itself. So a lot of those tools are still in development now, and we're rushing to the end to be able to use them. So at least for the baseline mission, we would be, if we can release results from the 3-point function, we'd be very happy. I don't think we're going to do it in 4-point though.
You talk about the data analysis challenges of doing power spectra, 3-point power spectra, L70,000. That sounds impossible, but
you mean on the cosmology side?
yeah.
Or
Yeah, how are you actually extracting? What are the computational requirements? What algorithms need to be developed? Machine learning?
that's a long topic. Yeah, there are many challenges. First of all, we have to produce all the redshifts and test the redshifts. The other thing is we're mapping structure on the sphere. And so as it turns out, most large scale structures are doing flat sky approximations. So you have to have developed special code to do it on a sphere. And then we also have to do this for the bispectrum. So that's just the computational part. Of course, all these things also have to have simulations to validate that they work. And we also have to put in, fake sources and so forth to validate, understand the properties of the measurements. So there's actually injected fake sources all over the sky. And then there's, systematics. Especially with the power spectrum, most of the information is coming from large scales. And in angular scales, it's sort of like 30-degree structures. So we have to understand the properties of the instrument and any systematics that can give additional, large scale structure, like absorption from the galaxy or other effects. So there's certainly a lot to worry about in the analysis. That's the short answer. I can write a book about things you have to worry about.
Any other questions before I ask you about Comet 3i Atlas?
3i Atlas.
You observed it. What did you find?
Yeah, so we observed 3i Atlas. For those of you unaware, those few of you who are unaware, 3i Atlas is the third known, maybe there are more, interstellar object. It's on a trajectory to exit the come into the solar system and exit the solar system, and on a hyperbolic orbit. We observed 3i Atlas, and we made some special allocations to do that because it's moving. We wouldn't get a complete spectrum, so we added some additional fields to complete the spectrum. And the short summary here is you can see pictures taken at various wavelengths. Here in the optical, we see it as a compact source. And this is a preliminary analysis, by the way. We have a paper coming out with a full analysis, but most dramatically, at this wavelength band, suddenly there's this huge coma of carbon dioxide gas. So that was pretty cool to see. And here you can see the brightness here in the optical. It's getting fainter, and then suddenly this bright coma. And this coma is huge in angular extent, and then disappearing again at the longer wavelengths. It was also observed, okay, yeah, and you can see the extension. It goes all the way out to like more than 300 arc seconds. And then it was observed by JWST a little bit before us, but we got our paper out first. And it's quite consistent with what JWST sees here. Bigger telescope, a little more sensitivity, a lot more sensitivity. You can see features here from water emission and the ice, as well as CO. And so we have, on further analysis, we do see these features weakly as well. But the CO2 feature with JWST is in a 3 arc second pixel. So just this very inner region. And so the, wide field of view with SPHEREx is always complementary to this, fine scale, high sensitivity, large telescope with JWST. Now, 3i Atlas is gone behind the sun and is coming back. So in December, we'll observe it again. We also have some special fields to hit it again. The interesting thing about this object is it has obviously a lot of CO2, but very little water vapor or CO at this time. Very unusual for a comet. It's not too surprising, I suppose, that it would be unusual. Our theory is actually it was heavily processed in whatever solar system it came from. But we'll see how it evolves, and we'll have more measurements in December.
Okay, well, thank you, Jamie, for coming down. Screen share. There's leave the meeting.